Very good morning, students. Welcome to the another session of irrigation and hydraulic structure subject. In the previous lecture, we have discussed about what is a mass inflow curve and how a mass inflow curve is prepared, and we have seen an example also how to estimate the storage capacity required for a reservoir for a given inflow values in the form of discharges. So that particular example is seen in the previous lecture. In the similar fashion, we have also discussed what is sedimentation, how the sedimentation is forming, how it is measured, and what are the different types of heads acting in the form of sediment load that we have discussed in the last class. Now, in the next topic, we are going to discuss about what is the life of a reservoir, how a life of a reservoir is estimated. In the estimation process of a life of a reservoir, what are the different steps involved? What are the factors which are governing the life of a reservoir? And also, we will also see how a life of a reservoir is estimated based on what parameters and when the life of a reservoir will be terminated. So, these particular points we will see in the coming slides. Now, before going to the topic, right, it is very essential that to calculate the life of a reservoir, how the life of a reservoir is estimated, it is very important point, right? So now let us get into the topic. See, if we calculate what is the ultimate density of a reservoir, means what is the ultimate capacity of a reservoir, that includes the silt content. Means whenever we say the ultimate density or ultimate capacity of a reservoir, that is including the silt deposition, because we are considering the silt deposition, the rate of silting while planning a reservoir. So the ultimate density of a reservoir is obviously includes the rate of sedimentation or sedimentation deposition in the reservoir. Okay, now how a reservoir, let us assume the reservoir is completely filled with the silt, but it takes very large number of years. Means the life of a reservoir will be terminated whenever the capacity of the reservoir is, the storage capacity of the reservoir is reduced to 20%. If it is reduced to 20%, then it is assumed that the life of a reservoir will be terminated. Means initially we have planned the reservoir in such a way that it is including the dead storage, means the storage for silt deposition. So if the more silt is forming, what happens? The reservoir capacity is reduced gradually. As we have given a slot for dead storage, which is for storing a silt, sedimentation deposition, but if the more deposition is there, if more silt is forming in the reservoir, it will come above the dead storage. So if it is beyond the dead storage, what happens? The useful storage or the live storage of a reservoir is considerably reduced. Okay. So it is clear that if the dead storage, if the storage capacity of a reservoir is reduced to 20% of the designed capacity, then it is considered as the life of a reservoir is terminated. So before planning a reservoir, while planning a reservoir, it is very essential that we need to consider what is the probable rate of silting in a reservoir, in that particular reservoir. So that consideration should be given, importance should be given for the rate of silting also. Otherwise, we may not expect the reservoir up to our life. Means whatever the initial life of a reservoir is expected, it may be 80 years or 100 years, that life will be decreased. The life of a reservoir will be decreased. So, to increase the life of a reservoir, we need to consider what is the probable rate of silting while planning itself. It is very essential. Okay. Now, moving on to the next slide. See how a reservoir, life of a reservoir is estimated. Right? It is completely dependent on the rate of silting. How the rate of silting or sedimentation deposition is estimated. The deposition sedimentation is estimated based on the trap efficiency of a reservoir. Means trap efficiency is again, it is a percentage in which the inflowing sediment is retained in the reservoir. Means what is the percentage of inflowing sediment which is retained in the reservoir. Right? So that is how we will calculate the trap efficiency. Trap efficiency is a function of two important factors, that is what is the capacity of a reservoir and as well as what is the inflow rate of sedimentation of a reservoir. Means what is the inflow rate, means how much amount of sediment is carried during the inflow, what is the rate of inflow of sedimentation, and what is the capacity of the reservoir. So based on these two factors, capacity to inflow rate of sedimentation, what we will do, we will calculate the trap efficiency. This trap efficiency is a function of two important factors. Please remember this point, this is very essential. Now moving on to the next slide. See here what we are doing based on the statistical data available. Means a survey is conducted on different ponded reservoirs, small ponded reservoirs, and a graph is prepared. Means how the trapped sediment is varying along with the capacity to inflow ratio. Because we have seen that trap efficiency is a function of capacity to inflow rate. Okay, so now this particular graph is showing you that the trap efficiency, means the percentage of sediment deposition is decreasing with respect to sediment deposition. Means if the deposition of sediment is increasing, what happens? The capacity of the reservoir is decreased. If the capacity of the reservoir is decreased, what happens? Ultimately the trap efficiency, means whatever the amount of sediment formation in the reservoir will be reduced. Why? Because in the initial stages of a reservoir, there is no silt in the reservoir. So there is a higher rate of silt is forming in the reservoir during the beginning stages of a reservoir. So as the time passes, the silting takes place in the reservoir. As the silting takes place in the reservoir, the rate of silting in the reservoir will be decreased. Means whatever the amount of sediment trapped. So as the time passes, this trapped efficiency, the sediment trapped will be decreased. Because in the initial stages, it is more. But later on as the time passes, the trap efficiency is decreased. That is how this curve is showing. That is what it is showing. It is a statistical data, analytical data, a survey conducted on the small ponded reservoirs. So the trap efficiency N is decreasing with respect to the shortfall or reduction in the storage capacity of a reservoir due to the sediment deposition. Because obviously we know that if a sedimentation is there in the reservoir, obviously the storage capacity will be reduced. If the storage capacity is reduced, what happens? Ultimately the trap efficiency is decreasing. The percentage of sediment trapped will also be going to be decreased. Okay. Now let us see. Let us take an example of two different cases. One is if a small reservoir is constructed on a large stream. A small reservoir is constructed on a large stream. So in this particular case, what we can observe is reservoir is small, but the inflow is very high because we have constructed a small reservoir on a large stream. So in this particular case, what happens? The capacity to inflow ratio, whatever the capacity to inflow ratio is there, that is very small, because inflow rate is more than the capacity of a reservoir, because the reservoir is small. So if the capacity to inflow ratio is decreasing, why it is decreasing? Because whatever the inflow is coming to the reservoir, because of lack of sufficient capacity of a reservoir, the reservoir is allowing the water to downstream side. Means we are not giving enough time to settle down the sedimentation because of the lack of capacity, lack of sufficient capacity of a reservoir. Whatever the sediment transported along with the inflow of a water, that amount of water will be sent to the downstream side of a reservoir. So this allows us what? There is no settlement of particles. We are not giving sufficient time to settle the floating particles, fine deposition. So they will be moved out of the dam by proper vents like sluice ways. So this is decreasing the trap efficiency of a reservoir. In what situation? If the reservoir is small and the inflow stream, whatever the stream is there, that is very large. So in this particular case, the trap efficiency is very less. Okay. In the next condition, the reverse condition, let us assume we have constructed a large reservoir across the small stream. So in this particular case, the capacity is more, but the inflow rate is very less. So in this particular case, what happens? The trap efficiency, the capacity to inflow ratio will be increasing because the inflow is small, capacity is small. So in this particular case, the capacity to inflow ratio is very high. So this particular situation allows the sediment to deposit for a longer longer periods of time, because as the capacity of a reservoir is more, what we are doing, we are giving sufficient time to settle down the sedimentation particles, because we are not releasing the water whenever the flow is coming to the reservoir, because we have sufficient capacity to store the water as the reservoir is large. So as we are providing sufficient time to settle down the particles which are coming along the stream into the reservoir, so the trap efficiency is always increasing in this particular situation, because we are giving enough time to settle down the water. Okay, so these are the two important cases we need to understand. We should have an idea at what situation we are constructing the dam, whether a large stream is there and we are constructing a small reservoir, or else on a small stream we are constructing a large reservoir. So this particular information will give you whether the trap efficiency will be increasing or decreasing. Okay, right? Now let us move on to the next slide. How a life of a reservoir is calculated based on a step-by-step procedure, right? So let us go into the first step. How a life of a reservoir is estimated. First thing we need to calculate what is the inflow rate of a reservoir. Means what is the inflow rate, how much inflow is coming to the reservoir, that should be calculated first. So let us assume we have a known quantity of inflow rate. Inflow rate is calculated. Now based on the inflow rate, what we have to do, we have to calculate capacity to inflow ratio. Means initially we are assuming that the reservoir capacity is full. Now with respect to full capacity and the inflow rate, we have calculated the trap efficiency. Now we have one trap efficiency value. Now let us assume the silt, whatever the capacity of the reservoir is there, that is divided into some intervals. Let us assume the silt is occupying the 10% storage capacity of the reservoir. So as the silt is occupying, what happens? The storage capacity of the reservoir is reduced to 90% only. Right? Now in this situation, what we have to do, again we need to calculate what is the inflow rate of that particular interval of time, and also we need to calculate what is the trap efficiency. Means capacity to inflow ratio we need to calculate for the reduced capacity of a reservoir and the inflow rate. So after calculating the capacity to inflow rate, we need to obtain the trap efficiency. Now we got two trap efficiencies. One is when the reservoir is having full capacity, and the second one is the reduced capacity of a reservoir up to 90%. Now let us take the average of these two. Full capacity, at full capacity of the reservoir, what is the trap efficiency, plus what is the at reduced capacity of a reservoir at 90%, what is the trap efficiency. Now we have take average of these two. Now let us assume we have taken the average of these two. Now in the next step, what we have to do, we have to determine what is the sediment inflow rate. So we have, let us assume we have the sediment inflow rate. Now that is calculated based on taking the different samples at different depths. So samples of water is collected, and after collecting the samples of water from the reservoir, what we have to do, we have to dry that sample, and after drying the sediment is calculated. So that we will be knowing this much amount of kilonewtons of sediment is forming in the reservoir for a given inflow rate. Now we have calculated the inflow rate. Let us assume now what we need to do, we need to multiply whatever the quantity of sediment is there. So that we need to convert it into hectometers, right, by dividing volume of whatever the volume of inflow rate is there, that is divided with the specific weight of the sediment. So whatever the inflow rate is there, that is divided with this, and after that we need to convert that into hectometers, volumetric units. So let us assume we have converted this into hectometers, volumetric units. Now in the next step, what we have to do, we need to divide the volume interval. We need to divide the volume interval. What is our volume interval? We have assumed that the 10% interval, 10% of the storage is reduced. So for that interval, 10%, whatever the amount of interval is there, volume of water is there, that is divided with the sediment transported, sediment deposited annually, which is denoted with ST. So after dividing the volume interval with sediment deposited ST, then we will be getting the value of number of years. Means how many years it took to form a 10% of the reservoir storage capacity. Means whatever the silt content, 10% is assumed, that much amount of silt is formed in this particular period of years. Means it took this many years. So we will be getting, right? So as for 10%, let us assume 5 years or 6 years we are getting. Then after this, what we have to do? Similar fashion, 10%, 20%, 30%, 40%, up to 80% we need to assume. So whatever the same procedure is adopted, we need to take the averages of the successive volume intervals, and we need to calculate the sediment deposition rate, and after that we need to multiply with that, and after that divide the volume, each volume with the ST, sediment deposition rate. Then you will be getting number of years for each interval assumed, 10%, 20%, 30%, up to 80%. Now, up to 80% we need to consider, because 80%, if the capacity of a reservoir is reduced to 80%, means 80% is occupied with silt and the 20% storage is available in the reservoir. If the reservoir capacity is reduced to 20%, right, of the designed capacity, initial design capacity, then it is assumed that the life of a reservoir is terminated. Then initially we have assumed a 10% silt formation, then later on 20, 30, 40, simultaneously up to 80% silt formation. Now let us add these all years, number of years, right? So after adding whatever the total number of years is coming, that is considered as the life of a reservoir. Means from full capacity of a reservoir to up to 80% silt formation will be the life of a reservoir. So that is calculated in this step-by-step procedure. So now to understand it in a better way, let us take an example of this particular trap efficiency. Now let us see the problem. Now this is the problem. What is the problem? It is given, there are certain trap efficiency values are given with respect to capacity inflow ratios. Now here what he is asking, the following information is available regarding the relationships between trap efficiency as well as the capacity inflow for a reservoir. Now he is asking us to find out what is the probable rate of life of a reservoir, probable life of a reservoir, that we need to find out, right? And also here he has mentioned that in the initial stages, means we need to find out the probable life of a reservoir with initial reservoir capacity as 30 million cubic meters. And also he is given that if the annual flood inflow is how much? 60 million cubic meters. And the average sediment inflow is considered as 3600,000 kilonewtons. Okay, so this is the amount of sediment is coming into the reservoir. Full stop. And again what he is giving, assume a specific weight of the sediment which is equal to 12 kilonewtons per cubic meters. The useful life of a reservoir will be terminated when it is reached to 20% of the designed capacity of a reservoir. Okay, now let us go to the solution. Now, initially what we need to do, we need to calculate what is the sediment, how much sediment is coming and what is the sediment inflow rate. So we need to calculate the sediment inflow rate first. Now, how to calculate this? The annual sediment as inflow, which is given as 36 lakhs kilonewtons. So this is, we need to convert it into, what is that volume of sediment inflow? It is given, weight is given in kilonewtons. Now let us convert it into volume. How to convert that? We need to divide the what is the average sediment which is given 3.6 into 10 to the power of 6 divided with the specific weight of the sediment. Now after dividing, we will be getting 0.3 million cubic meters. Now we have volume of sediment inflow. Then after that, what we need to do? We need to calculate what is the initial reservoir capacity. What is the initial reservoir capacity? Means there is no silt at all. What is the initial reservoir capacity? Let us assume that 30 million cubic meters is given and the inflow is given as 60 million cubic meters. Now let us calculate the capacity to inflow ratio. What is the capacity to inflow ratio? Right? So the capacity is given as 30 million cubic meters and the inflow is given as 60 million cubic meters. The capacity to inflow ratio is, we are getting as 0.5. Right? Now here one thing we need to observe that as the ratio decreases, capacity to inflow ratio decreases, the sedimentation, as the sedimentation takes place, the trap efficiency is also simultaneously decreasing. That we have seen in the standard graph. So that thing you need to keep it in mind. Now, here the volume of interval means we need to assume initially the capacity is 100%. Now we have to reduce capacity. So that volume of interval is chosen as 6 million cubic meters. Means initial capacity of the reservoir is 30. Now in the next stage, what we need to assume, the reservoir capacity is reduced to 24 only. Then later on 18, later on 12, later on 6. So like that we need to assume the interval of volume of interval is chosen as 6 million cubic meters. Please keep it in mind. Now let us move on to the tabular column. Now this is the tabular column, right? Where we have capacity in percentages 100 to 20%. Then we have volume in terms of cubic meters. Okay. So initial, what is the initial capacity of the reservoir? Initial volume of the reservoir? It is 30. As we have assumed the volume interval as 6, in the later stages we need to reduce it to 24, 18, 12 and 6 simultaneously. So we have assumed 6 million cubic meters as the volume interval. Okay. Now in the third column, what is there? The capacity to inflow ratio. So initially the capacity to inflow ratio is 0.5. 30 divided by 60. It is 0.5. So later on, what we have to do? We have to calculate for the reduced intervals also. Reduced storage capacities also we need to calculate what is capacity to inflow ratios. Okay. So 24 divided by 60, 18 divided by 60, like that we need to calculate. Then if we go to the next column, that is trap efficiency. Here you need to pay attention. The trap efficiencies are calculated based on the values available. Right? So this particular trap efficiency can be calculated with the available data. So for that I am moving. So this particular figure. So if we know the capacity to inflow ratio, we can calculate with respect to this curve, we can calculate what will be the percentage of sediment trapped, means efficiency of that particular sedimentation trapped efficiency. Now here let us assume from this graph we have calculated, that is 9675, means whatever the with respect to capacity to inflow ratio we have assumed from the curve, right? So for the capacity to inflow ratio of 0.5, let us assume we got the trap efficiency as 0.96. So similarly for the 0.4 capacity to inflow ratio, it is 0.955. So simultaneously we have calculated, by referring to the curve we have got these values, trap efficiency values. Now after this, what we need to do? We need to calculate what is the average trap efficiency for the interval assumed, means between 30 to 24 right capacities. Initial capacity is 30 and after reduced capacity, the capacity is 24. So in this interval of time, what is the average trap efficiency for that particular period of time? So let us take the average of 0.96 as well as 0.955. So the average is coming as 0.9675. So simultaneously, you have to take the average for all the intervals. So all the intervals are calculated here. Now let us go to the next column. So here the next column is indicating that annual sediment is, what is the annual sediment trap, which is indicated with ST. So how the annual sediment trap is calculated? It is calculated based on what is the inflow rate of sediment, that is multiplied with the average trap efficiency that we have calculated in the previous column. Okay, so here the average trap efficiency is, for the first interval assumed, is 0.9675. And what is our inflow rate for the first one? It is 0.3. 0.3 is the inflow rate of a reservoir, which is given in the problem. Now multiply 0.3 with 0.9675. So whatever the value you are getting, that will be your annual sediment trapped in the reservoir for that particular volume and for that particular interval of time. So simultaneously you need to calculate for the remaining also. 0.3 multiplied with the average efficiency is calculated for the different volume intervals. Okay. Now the last column is showing that you need to calculate what is the years, number of years to fill this particular volume. Right. So for this, what we need to do? We need to divide the volume interval with ST, means whatever the sediment, average sediment trapped, annual sediment trapped. So what is the volume here? Volume of interval, which is assumed as 6 million cubic meters. So 6 million cubic meters is divided with first interval. What is the first interval? Average trapped sediment. It is given as 0.2872. So 6 is divided with 0.2872. Now we will be getting the years as 20.9. So simultaneously you need to calculate for the remaining volumes of interval. They are divided with the average annual trap efficiency, annual average sediment trapped. So you will be getting the years for different volumes, right, after dividing. Now if we add all the years together, then whatever the total is there, which is 85.4. So those accumulated number of years is your life of a reservoir. Because why we came to conclusion that this is the life of a reservoir? Because whatever the volume interval, whatever the percentages we have assumed, it is from 100 to 20. So initially the capacity is 100%. Later on it reduced to 80. Later on it reduced to 60, 40 and 20. So if a reservoir capacity is reduced to 20% of the design capacity, right, then we are assuming it as a what? The life of a reservoir should be terminated. So this will be the 85.4 is your life of a reservoir. We can round it off to 85. So hence the life of a reservoir is 85 years. Okay. So this is how we need to calculate. We need to estimate the life of a reservoir. In the next class, we will be studying about dams. What a dam and what is the definition of dam and what are the different types of dams, what are the different classifications of dams based on different factors involved, and also we will be seeing about what is the selection criteria for a dam, how a dam is selected based on the different factors, and how a site for a dam is selected, what are the factors governing. Let us see in the next classes. Till then, thank you so much.